Hello, everybody. I'm very happy to introduce today Professor Jiménez, his academic degrees are aeronautical engineer in 1969 in Madrid. He got the Master of Science in Aeronautics in 1917 in California Institute of Technology and the PhD in Applied Mathematics in 1973, also in Caltech. His professional experience is since 1991 to present, he's professor of fluid mechanics in School of Aeronautics in Madrid. And he had different previous positions as visiting fellow, senior research fellow, professor of mechanics, in France, lecturer or assistant professor, etc. The several awards, and I will cite just a few. He is a member of the Spanish Academy of Science since 2008, member of the Spanish Academy of Engineering. He got the grants from the European Research Council, advanced grantee. He got the prize from a biennial fluid mechanics prize of Euromech and many other prizes. He has got 139 international refereed journals, and he directed more than 15 theses. So we are very happy to listen, Javier, his presentation dealing with the paper published recently in Physical Review Fluids. Thank you.
Okay, let me share the screen. Okay. Good morning or afternoon or evening or whatever. I'm very happy to be here. Thank you for the opportunity of doing this. Let me introduce this paper just a little so that we can start discussing later. This is a paper that has to do with the collective structures in decaying two-dimensional turbulence. This is the official title of the paper, and most of the discussion is going to be on that. And then I also want to say a little about how did I get into this, or why I start worrying again now about 2D turbulence, how to find them, okay? So, okay, this is 2D turbulence. I'm sure that everybody knows about this. This is mostly a computational thing because there are very few two-dimensional spaces in the universe. So you have a two-dimensional piece of the plane. In this case, it's a doubly periodic square. And you put some vorticity there, stir it, and then the vorticity concentrates into these little cores that interact with each other. And this is two-dimensional turbulence. This is mostly a theoretical thing, okay? But it is not completely useless because there are things on Earth, basically, and on planets which are thin. They're not quite two-dimensional, but thin, like oceans and the atmosphere. And then they more or less behave like two-dimensional turbulence. And we know almost everything about this. And we know almost everything about this because it's cheap. It's much cheaper than do things in 3 dimensions. So people have been looking at this for a long time. The basic thing that you have to know, the basic thing, the most interesting thing is shown here in this sketch. These are the spectrum. This is the spectrum of the energy spectrum of a two-dimensional flow. And here you have the energy, and here you have the wave number. So the small scales are here, the large scales are there. And if you force somewhere in between the smallest and the largest scale, then the energy goes to large things and the vorticity goes to small things. And this is different from three-dimensional case in which things only go down, okay? And, okay. This forward vorticity cascade, this is okay. I mean, we more or less understand that. This is basically these vortices is grinding against each other and stretching each other. But the backward energy cascade, it has always been less clear. It is mostly known what it is not. It's not a merging of vortices. It's a larger scale thing. Okay, so I started looking at this. Okay, and I mean, how do you look at this? Well, you can think, or you can ask the computer. And because I've been playing with computers for some time now, I decided to ask a computer. And I mean, that essentially means for the computer to try everything and try to find out which small scale features have a large scale influence, because this connection between the small scales to large scales, this is what the inverse cascade will be, something like that. And the computer, I cannot tell you this today, it's too long, but these two papers that you can look at if you want. And the computer came out with two suggestions, okay? And basically said, okay, well, look at vortices. And we knew that. I mean, the idea that turbulence is a vortex gas, that's a well-known theory, and it has been agreed on in the 1980s. And then it says something else which was new. I mean, to me, it was new. It says, okay, well, look at dipoles also. Not only individual vortices, but pairs of vortices, counter-rotating vortices. So those seems to be important. I mean, they seem to have a large scale influence. And this was less well known, which made it interesting. It was sort of a collective structure, and you expect something like this to be important if you are looking at how things get large. Okay, so I started looking at dipoles. Okay? And how do you look at dipoles? Well, the computer has limits. Okay, the computer says, okay, well, this looks important, but then it's up to you to think. And we know how to do that. I mean, this is a standard scientific method. So you with the hint that look at dipoles, you start looking at dipoles and try to see where they are, what they do, and things like that. Okay, and this is basically what this paper in physical fluid is about. And there's a previous paper in GFM, which also on some other aspects of this. Okay, so what comes out? Well, there are vortices. I mean, we also know that two-dimensional turbulence is a game of vortices, but the vortices come in two families. There are the small vortices and large vortices. Okay, you look at the probability density function of the size of the circulation, in this case of the vortices. There are two ranges in the PDF. There's a range of small vortices, which follows a power law. And whenever you see a power law, it implies a self-similar process, a self-similar amalgamation processes, things like two vortices of size 1, they merge into size 2, two vortices of size 2, they merge into size 4. So this is basically what people have mentioned, because most of the vortices are small. But then there are a few large vortices. There are a few large vortices, and they have a distribution which is not a power law, it's an exponential. Okay, and exponentials are different. The exponential means that there is a scale. There has to be a scale because you need a scale in the exponent. Okay, and this is vortex of size 1. Okay, and the vortex of size 1 are being accreted into the large vortices. Okay, so there are two different things. So you look at this in time, what you see is that this limit between one and the other keeps moving, so that vortices amalgamate and they're eventually sucked into these large families of vortices. Okay, and these two families are different. They don't only have a different distribution and a different origin. They have a different dynamics. You have this plot here in which what you have are the vortices, and here you have the average mobility of the vortices, how fast they move around. Okay, and here you have the kinetic energy associated with the vortices, how much are they moving the fluid around them. Okay, so you look at the small vortices, they're like a vortex gas. They move around fast. Okay, and they have no energy. Okay, they have a very small fraction of the energy. And you look at the large vortices. Well, this is where the dipoles is. They have most of the kinetic energy, but they move slowly. And if they move slowly, they cannot be moving individually. They have to move slowly because somehow they are locked to each other. I mean, they see each other and they cannot move. Okay, so this is a collective structure that is dipoles. These are a good candidate for the large scales, and that means that there has to be an organization, and there is an organization. These vortices, these dipoles, they tend to form dipoles, and then these dipoles become organized into streams, into like things in a necklace. Okay, and there will be a dipole here, and there will be another dipole there, and what they do, they get these long streams. Okay, and these long streams now they are large. Okay, and the reason that these streams are elongated and large is why there is an influence of the small scales into the large scales. Because if you think of it, you have this system of streams and dipoles, and you do something with the dipole here. You block the stream, and then you're blocking the whole river. It's like you put a dam in a river. It's not only gets dry near the dam, it gets dry all the downstream part of the river. Okay, so this is the link between the small and large. Okay, the formation of these streams. Okay, and well, why do vortices? Why do dipoles form, and why did they organize each other? Well, they do it because they're trying to minimize energy, which if you are in a dissipative system like turbulence, viscous turbulence, is a reasonable thing to do. And you can see that they're trying to form dipoles, and they minimize energy. They minimize energy by screening each other. Vortices have a sign, so you have a single vortex. That has a lot of kinetic energy because it moves fluid all over the universe, basically. Actually, the kinetic energy of a single vortex is infinite. And if you, but you have a pair, this vortex sort of cancels this one, and then from far away, you see something much weaker. And you can test that this thing is happening, that the things try to get organized into these counter-rotating dipoles, but looking at the correlation function between the circulations as a factor of distance. And then when you do that, you get these solid lines here that have a minimum, and the minimum is negative. And that means that you have a positive vortex here. You tend to have a negative vortex there. And this is basically the main distance between vortices. And this is a property of the flow, a property of the organization of vortices in the flow, not the properties of a system of points. Because if you take the same vortices and randomize them, put them in random position, what you get is all these dashed lines, which have no minimum there and have no structure. And now you think that you're trying to organize yourself, and you have to find a partner of the opposite sign. And this guy also has to find a partner of the opposite sign. There has to be some larger scale organization of this, okay? And actually there is. These things form something like that is close to a crystal, okay? And you can check that, for example, you take your vortices, your large vortices. I mean, I have taken the small vortice away. You take your large vortices, substitute them by a point in the center of gravity, partition the plane into things which are basically the nearest neighbors of each point in here. This is called a Voronoi tessellation. And look at the size of the tessellation. I mean, which fraction of the plane is associated to each vortex. And you get a distribution of sizes, which is something like this, these black things here. These different lines that you see here, different Reynolds numbers, and they all agree very well, okay? And this is, okay, you see that they're not the same, but they're much more uniform than what happens if you take the same points and, randomize them, where you get this wider distribution. So you get something like a vortex crystal, and that sounds funny, but it's not actually. Vortex crystals are quite common. This, for example, is a picture of the north pole of Jupiter, and you see there is a vortex hexagon there, which is more or less permanent. This is something that you don't think of as a vortex crystal, but it's a vortex crystal. It's a wave, okay? And vortices get put into these positions here, and then they stay there for a long time, okay? This also happens in two-dimensional plasmas, magnetized plasma, and even in forced two-dimensional turbulence, which is different from decaying turbulence, because now turbulence has all the time in the world. This is infinite time. All the time in the world to crystallize if it wants, and it does, okay? Yeah, you see here, there is this small details here. This is the forcing in this case. Turbulence is being forced at this small scale. And the large vortices have formed, and they form this very, very clean lattice there. Okay? So let me summarize and let's finish and go to the questions. The main conclusion here is that the inverse cascade is a collective structure, and the collective structure into the turbulence is organized by way of dipoles. The dipoles, they are like that because they screen each other, they form streams, they form crystals. And something that to me was cute in this case is that basically it was a computer-enabled discovery. I have been looking at 2D turbulence for 40 years myself, and I never thought of streams. Dipoles were there, yes, but who cares about them? Well, you have to care about them. So this is it. We'll go to questions. And by the way, I'm looking for PhD students if you have any. Thank you.
Thank you very much, Javier, for this very nice talk. So we may go to the session of questions now. So please, yes, thank you. So please raise your hand if you have questions, or you may ask them in the chat. I do not see questions, so I may start. Maybe the time for people to think of questions. Javier, I have looked at your paper, and I have one question concerning the self-similarity. So as a general issue, you show in 2 or more figures that is the scale that you call lambda p, that you built on the basis of a Poisson distribution. That is this scale lambda p that allows for different curves to collapse on a single one. For instance, in your figure 1, you show the mean distance between 2 successive large vortices, or the diameter of these large vortices. So this scale allows that. Why do you think that happens? Is that linked to the equations or whatever? Or how do you explain that?
Well, that lambda is basically, it counts the number of vortices that are in the,
yes,
in the box. And that keeps changing with time. I mean, there is a plot somewhere, I think in figure 1 or 2, where you see that this lambda growing with time. But the vortices keep merging with each other. There are fewer and fewer vortices. And then the mean distance between vortices keeps growing. And at the moment in which I see that distance being of the same order as of my computational box, I stop, because that's a different, a different regime, basically.
So you do not see any possible explanation as a similarity scale from the transport equations?
No. That basically is something that changes with time. I mean, this is counting the number of vortices. And once you count the number of vortices, then the mean distance between vortices has to be whatever it has to be. And the mean, I mean, if you look at, you remember this plot here, you see this is the distribution of the size of the Vortices L, and they both have exactly the same mean value, which is 0.5, and it has to be 0.5 because this is not normalized with the number of vortices, and it just means that when the plane is divided on the mean.
Okay, so it cannot be in another way. But when you represent also on your figure 1, you represent lambda q and lambda omega as a function of this lambda p, we see 2 regimes. So this is related to what?
That basically, and let me remember.
Oh, you don't have that in your slides, I believe.
No. But I mean, basically the things grow self-similar until they bump into
yes.
into
they
the
touch the boundaries.
And
yes.
when they touch the boundaries, then it's a different regime, which is what many people have looked at, including me. I mean, because this initial inverse cascade is actually quite fast. It happened quite fast. It fills the box quite soon. And then you have a different thing. I mean, you have essentially a Hamiltonian system that merges everything now and then. But it's the Hamiltonian system of something which is always 18 vortices, which is basically when the size of the box fills, sees the number. 18 vortices, you think of them as 4 vortices by 4 vortices. So it basically fills the whole thing.
Thank you, Javier. We have one question from Alvaro Marin. Beautiful work, Javier. You mentioned that the dipole idea came from the computer. Do you mean you used something like a machine learning algorithm for that?
Yes, I mean that's a different. That's a different paper. Actually, a different for paper. This is what I am doing now. I'm trying to convince the computer to give us ideas. And basically what we do, and this is what my group is doing now, not only with 2D turbulence, but with 3D turbulence also. You do a lot of tests. I mean, you test every possible experiment that you can think of and see which ones look interesting, okay? And then, okay, then you get a list of interesting data. And interesting is something for you to decide, of course, but in this case, it's basically you change something now and something is happening later, okay? If something is happening later, then that is an interesting case, okay? And then there is a machine learning algorithm basically to tell us, to try to do classes of these original experiments that made a difference in the future, okay? And in this case, when we went through all the clustering and all that, they come out with 2 clusters. One was Vortices and one was Dipoles.
Thank you. We have one question from Beverly, please.
Hi, Javier. I enjoyed that very much. Thank you. You probably guess what my question is. Have you thought about extensions of this particular approach to 3D?
Well, we are doing that. I mean, they have 2 students doing isotropic turbulence, 3D isotropic turbulence, and 1 student doing a channel. Another one coming for wall turbulence. Okay. Of course, the 3D is the fun thing.
Right.
But I mean, the point. I mean, the point of doing 2D is I can run a simulation, a full simulation of 2D in 30 seconds. And this paper has 2 million simulations. Okay. Which sounds like a lot, but when you count that in computer time, is a lot. Okay. But then you develop techniques in 2D. Okay, you play as much as you want in 2D. Find out where are the pitfalls, where do you do things wrong. We did many things wrong, and I'm sure that we're still doing many things wrong. And then you move to 3D, where things are not terribly more expensive, but instead of 30 seconds, it's maybe 5 minutes. And then things become months, a year, okay? But yes, of course, I mean, 3D is the fun.
Yeah, I was just wondering where you were in the process. So great, I'll look forward to seeing that.
Okay.
Thank you.
Thank you.
Okay.
Do we have other questions?
I see Howard Stone there. It's a hand raise. No.
Yeah,
I have.
This is perhaps a question that's, you know, from someone pretty far outside the field, but my question was spurred by Beverly's remark. You did 2D, and by that you really mean perfectly 2D.
Yeah.
And then of course people talk about 3D turbulence. My impression, and this might be my ignorance, is that when people model certain problems that look 2D, it's really actually a 3-dimensional domain that's thin. And I guess my question is, does any part of that thinness, which is sort of a real feature of 3D, when you project to 2D, possibly introduce new terms that would modify what you're thinking about when you make a perfectly 2D model of 2D turbulence?
Okay, I mean, 2D turbulence, perfectly 2D turbulence is a theoretical problem that actually people look at it because a long time ago in 1949, Sager said that if you look at that from the theoretical point of view and in the implicit limit, it's a Hamiltonian system that it is, okay, we know that, okay? And it should be should have negative temperature, okay? And this negative temperature is the thing that gives you large scales, and this is actually the thing that is behind the inverse energy cascade, okay? So this is why people do 2D turbulence. It's very different from 3D turbulence. There is, I mean, for one thing, we know in this case that the Navier-Stokes solution, the Navier-Stokes equation have a solution. I mean, this is not a problem here anymore, okay? If you're looking at these thin problems like the atmosphere, okay, and the atmosphere is like 10 kilometers by 10,000 or something like that, then there is a range of scales, which is basically a range of scales of highs and lows, atmospheric highs and atmospheric lows, which is essentially 2D. The 3D the 3D influence there is very small. If you get smaller than that, unfortunately, of course, the Earth is going around. So in that range of scale, you also have a rotation and different rotation.
Okay.
But the experiments, the 2D experiments are not very 2D. The closest thing that I have seen to 2D experiments are these people that do soft films. They have a wind tunnel with soft films and then they put obstacles and things like that.
Thank you. Do we have other questions, or maybe I can continue with this analogy with Jupiter that you mentioned earlier and also in your paper, but now you simulate what you put in the computer is Navier-Stokes in a 2D with initial conditions, etc. But if we were to do the analogy with these flows, then we should add effects like rotation, stratification, or maybe magnetic field. How do you believe that could change your conclusions? Or still 2D, but...
Or yes, it will change it. I mean, that of course has been done. I mean, two determinants in the beta plane, which is the plane in which the rotation changes with. Well, I know that you know, but there might be people in the audience that don't know. Okay, it's a plane in which the rotation rate changes with the distance away from the equator to the pole. And that changes things a lot. That's where you get these streams, that's where you get things like well, not the jet stream, that's it different, but things like that, you get Rossby waves. I mean, Rossby waves change the flow completely. Still, I mean, there is also an inverse cascade, okay? And that has been done a lot. I mean, actually, dipoles, people in my community, a dipole is a dipole. For the physical people, is a modon. They even have a name for it, a different name for it. It changes, but the inverse cascade is still there. You want to know about the inverse cascade. And certainly there are streams, which there are called bands. Okay, like in Jupiter, you see all these bands. These are essentially streams, I think. And if you look at something like the jet stream, sorry, the jet stream, I was thinking of the, well, no, the jet stream, I mean, all these things have to do with stratification. There are streams, the Gulf Stream is the Gulf Stream, but this is where it is because America is there, it's in the middle of the stream. Yeah, it's a different, it changes. But it has been done a lot. I mean, there is a lot of work on that.
Okay, so I look if we have other questions from the audience or in the chat. I don't know, maybe if you can tell us a final word on the role of the initial conditions. I remember you discussed a lot and you argued that this inverse cascade at some point erases whatever you input initially as an infrared slope for your spectrum. And you seemed to suggest that it doesn't matter, or it does not have a lot of importance what I put initially as an infrared spectral slope, because the inverse cascade will do the job.
Well, I mean, eventually the inverse cascade will do the job. The question is whether it has time to do the job before it hits the box. Okay. If I start with an initial condition with a very clear length scale, for example, if I start with a spectrum that looks like this, okay, then what happens is these large vortices, they form at this scale, and by the time this thing gets organized, you still have these large vortices with that scale, because they don't have time to create. I played a little with this. I mean, I tried different infrared, infrared spectra, as you know. I mean, you were my editor.
Yes.
Okay. So, and it didn't. I mean, the same thing was happening, but I could break it. The whole idea, if I try hard enough to break it, I break it. Essentially, by putting single scale. Something that I never tried is put something with two well-defined scales, say 5, and 2. That will probably, again, be a different thing. At the end, you are looking at a Hamiltonian system. And the Hamiltonian system do whatever they want. I mean, they explore the whole phase space.
Thank you very much. And I believe we don't have other questions. We thank you very much, Javier, for this nice presentation, and we are looking forward to the follow-up of this work. And thank you, everybody, for your participation. Thank you. Have a nice day. Bye-bye.
Thank you.